In this lesson, we'll be talking about exceptions with Python. Exceptions essentially are runtime errors. Modern programming practice is to use exceptions for handling these runtime errors. An exception is a signal that something unexpected has happened to your running program. If not handled, the program will terminate abnormally or crash. Now, we've already seen exceptions before. If you recall, you used name error or type error or index error. Those are all exception types. So let's talk about examples of runtime errors that cause exceptions. Now, the ones we have seen are index out of bound for a list or a string, or division by 0. So let's create some code to create an exception. Here's a very simple 3-line program. The first line creates a list. Recall this is the repetition operator that repeats the contents of this list 3 times. So this will create a list of 9 elements. It prints the list, and then it prints an element of the list indexing into element 15. Now the list only has 9 elements, so this will obviously be a runtime error. So what is the default behavior when Python has a runtime error? The program will end and give you an error message, and will point you to the line number. So actually, let's try this out. We'll actually run it and see this happening. So we open up PyCharm, paste the code, and run it. So the first line is the list that is printed right here. Then it shows an exception. It gives you the line number. It actually gives you the actual contents of the line. It says this is an index error, list index out of range. Okay, another example. In this example, we only have 2 lines, and we are reading input and giving a prompt. Now recall, input always returns a string, and then we take that string and we try to convert it into int and multiply 10. Now this is another one that could give you a possible error if what you enter is not interpretable as an integer. So let's try this one out as well. We'll open up PyCharm, we'll replace our code, and if we run this to create the error, you would have to enter something that is not interpretable as an integer. So let's enter ABC. Now here you get, again, the line number, the actual contents of the line, and here you get a value error, invalid literal for int with base 10 ABC. Now another example is if you were to enter something that looks like a decimal, you would get exactly the same error, but for the decimal. Now, without the ability to programmatically handle the exception, your only choice is to go back to the program, change the code, and try again. To handle it programmatically, we need to use try except statements. This is a new control structure that gives us a way to process errors at runtime and to continue running the program. So what is a try except statement? What does its syntax looks like? It looks like the following. There is a try block and 1 or more except blocks. So in this particular case, statements S1, S2, S3 are part of the try block. Statements S4 and S5 are part of one except block, and S6 and S7 are part of the next except block. Statement S8 is after the try except statement. Now the difference between these 2 except blocks is the error type. Now how does this run? So when we run a try except statement, the try block is executed. If there is no runtime error, everything is fine, you continue execution after the try except statement. If there is a runtime error in the try block, the execution jumps to an except block that matches the error type that has just happened. And the statements of that except block are executed. Now, what if there is no matching error type available? In this case, the program will terminate abnormally, as we have already seen before. Now, there is an error type called exception, which will match all runtime errors, so you could just use that one. And let's actually see what an example of using a try except statement looks like. To add exception handling, we basically wrap the code that might have a runtime error within a try except statement. So here we have the same code from earlier where we were reading an integer that might cause a runtime error. We have wrapped it in a try except statement. Notice that try and except are reserved words or keywords. And then we're using colons here. So you would have a colon after the try, and you would have a colon after the error type. This particular program, the way it is written, will not crash regardless of input. And that is because when a runtime error occurs, it always finds a matching exception type, because exception is the most generic error type. So let's look at some possible inputs. For example, if we enter good input, such as like a -99, it will basically print the number multiplied by 10 and print continuing, which is the statement right after the try except. Now, if we did have bad input like ABC, it would jump to the except block, print that statement, and then still continue. Now, a more appropriate thing to do here is to use a more specific error type, such as a value error instead of the general exception error type. So I show that here, where we are now using value error. So let's actually try this out. We'll replace our code earlier, right? And let's run this. As I had said, if you enter a proper value like a 10, you will get 100, which is statement number 3 right here. If you enter an improper value, such as an ABC or something that looks like a decimal, you would see the line number 5, which says hello runtime error. Now the question I have here is, what would happen if you replace value error with type error, a different error type, one that doesn't match the condition that happens? So let's actually try that out. And if we run this and say ABC, for example, it prints the output that you see in a crash. Now, why is that? The reason is because there is no matching error type except block found. It is also possible to print the actual error that is happening instead of, hello runtime error. We do have a handle on the exception object that is raised. Now, how would you do that? So let's take a look at this code here. This is exactly the same as before. The only difference is we are using as E to capture the exception object. So now E will hold the actual exception object that has been created because of this runtime error. And then you can simply go ahead and print it. And so if we were to do that, let's copy that in PyCharm. And if we run this and say ABC, it will actually give you a more informative message that is associated with the exception object. That is exactly what I show here. So we've seen that there are two ways that a program could crash due to a runtime error. The first one is that there's no try except statement there in the program to handle the exception. The second is that there is a try except statement, but the error type that is occurring is not listed in an except block. So how does all this work with deeply nested function calls? So consider the following piece of code with 3 different nested calls. So the top level we have main, a call to main. In the definition of main, there is a prompt being printed, and this other function called read currency is being used, and its value is being captured. Read currency, in turn, prints a $sign as a prompt, then uses another function called read number, capture its value, and returns that. Further, in read number, we are using input and converting it to float, capturing that value and returning that. Now, this is the line where a runtime error could occur because input returns a string, which will be interpreted as a float, and that's where things could go wrong. So how do exceptions work with this nested hierarchy of function calls? So when an exception occurs, Python checks if there is a try except in the function where the runtime error has occurred that can handle this error. Now, if there is none there, Python will transparently propagate that exception to the calling function and check for a try except statement there. If none is found, it keeps on repeating this process till it reaches the top level. If still there is no exception handling code found, the program crashes, as we have seen before. So what does this look like if you're actually trying to run it? So here's a little transcript of me trying to run it with the value of ABC, which is obviously not a float. And it shows you the call hierarchy of reaching that point where the exception happened. So from the call to input up to call to read number, read currency, and main, and gives you all the line numbers. So obviously the exception is not being handled. So the question is, where should we put the try catch? Where is the right place to put it? Should we put it in read number here, where it's the closest to where it happened, or read currency, or in main? And that is a tricky question. And the answer is you would want to put it in the place where you have the most context to interpret what is going on and possibly recover from it. And the answer is main is the best place to put it, because that is where you know what you're trying to do and you are trying to read a currency amount. If you put it in number, yes, you would know that someone was trying to read a float, and that's when something went wrong, and it's not quite clear why they were trying to read a float. They could have been calling read number from a different context and not this particular context where you were trying to actually read some transfer amount. So what would that code look like? It would look like the following, where we would put the try except in main, and the particular kind of error we would get here is value error. And you could print something intelligent and say you did not enter a numerical currency value. Let's try again. You could have a loop here till the person actually enters a valid number. Now you notice this ellipsis here, dot, dot, dot. You would think that this is not exactly interpretable by Python, but this actually will compile and will run. Python uses the ellipsis to indicate some placeholder for incomplete code, right? So if you were to run this and enter a bad value, you would get a nice error message, and you might be able to reach a code where it actually retried to read the number. So the bottom line is exceptions give us a way to automatically propagate the exception to the right place where it can be handled, and we could continue execution. If you didn't use exceptions, how would you do this? You would probably have to return some error code back up, and there'll be a lot of messy code that you would have to create for that. It will make your program a lot harder to read. So far, we have seen exceptions that are automatically created by the Python interpreter, but you actually have the ability to create these or raise these exceptions yourself. For example, the same code what I've added here is that if we detect that someone enters a negative transfer value, that we'll actually create an exception or raise an exception ourselves. We'll create a value error, and we can even have a string here and include the amount that was entered and give a nice message saying that, hey, you entered a negative currency. And we can catch that and print the message here. So again, if you were entering a negative number here, you'd get a nice error message. So in summary, raise exceptions where appropriate, and then use try except statements where there is most context to be able to deal with the exception and possibly recover. Now there are places where we do not want to use exceptions. Specifically, don't use exceptions to replace good validation. So let's take a look at an example. Here we have a list L that is a list that holds numbers, and we populate it with some code. And then we want to calculate the average of the numbers that are in this list, and we would do it as following. Average is equal to sum of all the numbers in the list. You divide that by the length of the list, and that's where you might get a runtime error. And that would be because the list is empty. This code should be replaced by explicitly checking the length of the list and making sure that it is greater than 0 before you do this statement. Now we've already said that there can be multiple except blocks, each with a different error type. Now let's talk about a couple of new type of blocks. So consider this code. It's very similar to the one we've been using. Here we're prompting for an integer, reading a string, trying to convert it into an int, and then dividing 100 with that value. So now a couple of different kind of errors can happen. One is what's entered for x is not interpretable as an integer. The second is it is an integer, but it's 0, and so you could get a 0 division error. So those are the two error types listed in the two different except blocks. Now there's another block here, which is the else block, and a finally block as well. So what are these things? So the else block is executed if no exception has happened. The finally block is always executed regardless of whether exception happened or not. So what are these things used for? Let's take a look at this example. So we've already seen that if there's a value error, we can say, hey, this is not a number, division 0 error. You can't really divide by 0. You can use the else block here to actually print the correct value since no error has happened. And the finally is typically used to clean up or reset values. Now here we are resetting result to 0. So a couple of new type of blocks. The final thing I want to mention is that we've seen syntax error. And although this looks like value error or index error, this is not a runtime error. It is found when Python is parsing your program and it detects a missing colon or missing parentheses. Hence, this is not raised as an exception and can't be handled with a try except. So this has been a lesson on exceptions. Thank you.